Origin Quantum has built a single operating system that claims to run superconducting qubits, trapped ion qubits, and neutral atom qubits, three machines so physically different that building one control layer for all three is, by the consensus of most quantum engineers, somewhere between very hard and a mistake. IBM hasn't done it. Microsoft hasn't done it cleanly either. And yet here is Pilot OS 4.0, with documentation saying it does. Before you conclude this is marketing, a brochure checkbox listing 3 hardware types nobody has actually tested together. Stay with me because the interesting question isn't whether the code works, it's why you would build it this way at all, and what it tells you about where China thinks quantum computing is actually going. Whoever controls the software layer that developers and labs lock into before a hardware winner emerges, controls what quantum computing gets used for, regardless of which physical machine eventually wins. By the end, you'll understand why the 3 modalities are so different that one stack for all 3 is genuinely hard, what Origin is actually betting on, and whether breadth or depth wins during the uncertain phase of a technology race. This isn't really a story about an operating system. It's about who builds the floor the rest of the industry stands on while the ceiling is still being negotiated. To understand why a single control layer for all 3 is hard, genuinely hard, not just engineering speak for a lot of code, you need to feel the physical gap between these machines. Superconducting qubits operate at around 15 millikelvin. That's colder than the average temperature of outer space. The control electronics firegate pulses in nanoseconds, and the error profile of every qubit is tied to the electromagnetic noise in its immediate environment. The whole system is exquisitely sensitive to anything that disturbs that frozen electromagnetic landscape. Trapped ion qubits are a different world entirely. They operate at room temperature inside vacuum chambers, where individual ions hang suspended in electromagnetic traps. The gate speeds are measured in microseconds, roughly 1,000 times slower per gate than superconducting systems. But the payoff is coherence. Trapped ion qubits hold their quantum state far longer, and their error characteristics are fundamentally different because the noise sources are different. You're not fighting electromagnetic interference, you're fighting laser instability and ion heating. Neutral atom qubits are newer still. Individual atoms are held in place by optical tweezer arrays, beams of light acting as microscopic grippers, and they offer a reconfigurability that neither superconducting nor trapped ion systems can easily match. Companies like QuEra and Pasqal have published scaling results that have the field paying close attention. The control electronics, timing requirements, pulse shapes, and error correction strategies for each are fundamentally different. Think of it this way. Imagine building one universal remote control for 3 televisions that run on completely different signal formats. One speaks radio frequency, one speaks infrared with 10 times the bandwidth, one speaks Bluetooth with a self-reconfiguring antenna. You can absolutely build a universal remote, but every time you abstract away the format details to make it universal, you lose the ability to exploit the fastest path for each individual television. The question is whether the convenience of one remote is worth that speed sacrifice. Here's the honest answer to, can't software just handle the differences in the background? Some of it, yes. But the performance-critical quantum operations, error correction, qubit readout, gate scheduling, are exactly where the hardware-specific details live. Abstracting over them doesn't make the differences disappear. It means your software can't exploit them fully. So a one-stack system is either accepting a performance ceiling on each individual machine, or it's doing something architecturally clever to expose enough low-level detail through the abstraction layer. Which one Pilot OS 4.0 actually does is the question the vendor documentation needs to answer. What Origin's documentation describes is an orchestration and control layer, not just a circuit compiler, that handles job scheduling, qubit resource allocation, and back-end translation across all 3 modalities. The architectural claim is that Pilot OS 4.0 provides a unified programming interface while translating to modality-specific pulse-level instructions at the back end. That distinction matters. This is meaningfully different from just wrapping 3 separate compilers in a common application programming interface and calling it integration. If the claim holds, the translation is happening at the control layer, not just at the job routing layer. The honest framing of where the evidence stands, runs 3 modalities, is a vendor capability claim. The architecture description is plausible and consistent with known software approaches in the field. The depth of back-end support, whether all 3 modalities are production tested at comparable depth, or whether one or two backends are more mature than the third odds is not confirmed in the available record. No independent benchmarks showing fidelity results across all three backends appear in the public record. What we can say is that the architectural approach is coherent and non-trivial. Whether the implementation matches the ambition is the verification gap. Now compare this to what IBM and Microsoft have actually built, because the gap there is real, and it matters for understanding Origin's position. IBM's Qiskit is the dominant open source quantum software development kit. It is architecturally superconducting primary. The deepest optimization tooling, the most mature error mitigation, the tightest gate scheduling are all built around IBM's own superconducting systems. Qiskit includes a back-end abstraction layer that can, in principle, connect to other hardware via provider plugins. But purpose-built support for IBM's own machines is where the depth lives. Microsoft's Azure Quantum is structured differently. It's a cloud platform that routes jobs to partner hardware providers, including IonQ, Quantinuum, and Rigetti, covering trapped ion and superconducting backends. That's genuine multi-hardware reach. But Azure Quantum is architecturally a cloud marketplace. It sends your circuit to the partner's own control stack, which runs the actual pulse-level execution. The routing is Microsoft's, the control is the partner's. Based on available public documentation, neither IBM Qiskit nor Microsoft Azure Quantum natively supports neutral atom backends at production depth comparable to their primary hardware focus. That neutral atom gap, and it is worth stating clearly that this is a reasoned inference from what the public documentation shows, not an independently audited audit-E, is where Origin's claim position is most differentiated. If Pilot OS 4.0 genuinely orchestrates neutral atom hardware at the control layer, rather than the routing layer, it occupies a position neither of the two most prominent Western platforms currently claims as cleanly. If Origin has actually built deeper cross-modality control than either IBM or Microsoft, not just application programming interface routing, but pulse-level translation, that is a genuine differentiator. If it's closer to routing with a unified job queue, it's less differentiated but still a coherent platform play. The architectural ambition is distinct either way, which brings us to the strategic logic behind building this way at all, and why it might be right regardless of which hardware eventually wins. The quantum hardware field has no consensus winner. IBM has announced processors with over 1,000 physical qubits, a company-reported milestone that reflects genuine engineering progress in superconducting systems, though it is worth being precise. These are physical qubits per IBM's own framing, not error-corrected logical qubits, which are what fault-tolerant quantum computing actually requires. Trapped ion systems from IonQ and Quantinuum have demonstrated strong native gate fidelity and long coherence in published benchmarks. Neutral atom systems from QuEra and Pasqal have shown rapid scaling in optical tweezer arrays and algorithmic flexibility that neither of the other two modalities matches easily. Most serious quantum computing programs, national labs, large enterprises, appear to be hedging across multiple modalities rather than committing to one, based on public statements from those programs. Here is the pre-consolidation parallel that makes Origin's bet legible. In the early server operating system landscape, before a dominant platform emerged, organizations that built applications on proprietary stacks tied to one vendor's hardware found themselves stranded when the market consolidated differently than expected. The ones who built on abstraction layers that could run across multiple architectures kept their code alive through the transition. Origin is betting that quantum computing is in that pre-consolidation moment right now. The developer and lab lock-in happens before the hardware winner emerges, not after. Whoever owns the workflow, the tooling, the job queue, and the circuit library that research groups build on top of accumulate switching costs that survive hardware transitions. IBM is raising a superconducting ceiling, more qubits, better gates, deeper error correction. Microsoft is building toward a topological ceiling, betting that a different physical approach will eventually deliver fault tolerance more cheaply than any of the three current modalities. Origin is raising a platform floor, wide enough that if either ceiling wins, or if neutral atom leapfrogs both, the applications built on Pilot OS's orchestration layer don't have to be rewritten from scratch. That is a different kind of competitive position, and it only makes sense during the uncertain phase of the race. The floor isn't competing with the ceilings right now. It's making itself indispensable before anyone knows which ceiling matters. Here's where the two bets separate cleanly. Bet A, hardware agnostic orchestration, is the durable play. Flexibility becomes a moat as the field consolidates around whichever modality proves out. Users building on Origin's stack can migrate workloads to whichever backend matures fastest without rebuilding their application layer. Bet B. Abstraction is a performance trap. Superconducting, trapped ion, and neutral atom qubits have such different error behaviors that a one-stack-fits-all layer hides the details that matter most. And when hardware does converge on a winner, a purpose-built stack for that winner will outperform the generalist layer decisively. Both bets are coherent. The evidence does not decide between them yet. The triumphalist read that Origin has solved multimodality quantum control and leapfrogged IBM and Microsoft is not supported. Pilot OS 4.0 is a vendor capability claim with no independent benchmark verification across all three backends in the public record. The dismissive read that this is a brochure with nothing behind it is also wrong, because the architectural approach is coherent, the platform logic is sound, and the competitive gap on neutral atom coverage for both IBM and Microsoft is real based on what the public documentation shows. The honest read is narrower. Origin has made a credible platform floor bet at a moment when nobody else has staked out that exact position as cleanly. And whether the bet pays off depends on whether hardware convergence comes fast or slow, and whether depth or breadth wins the developer lock-in race. If the bet pays off, China's quantum software ecosystem doesn't get stranded if superconducting hits a scaling wall. Labs and enterprises building on Pilot OS can migrate workloads to whichever backend matures fastest without rebuilding from scratch. That's not a small thing. It's the whole point of building a floor instead of a ceiling. Here's my honest read. The verification gap on Pilot OS 4.0 is real. We don't have independent benchmarks showing fidelity results across all three backends, and vendor documentation is not the same as a peer-reviewed result. But the platform floor logic is sound, and the timing is right. The field is in the pre-winner phase. This is exactly the moment when platform lock-in accrues. If Origin's orchestration is as deep as the documentation claims, they've taken a position that neither IBM nor Microsoft currently occupies as cleanly, not because China leads on qubits or error rates or fault tolerance, but because they may be building the layer that outlasts whoever wins the qubit race. IBM is pushing its superconducting ceiling higher every year. Microsoft is building toward a topological ceiling it believes will eventually render the current generation of machines obsolete. Origin isn't competing on ceiling height right now. It's raising a floor wide enough to stand on regardless of which ceiling wins. That might be the smartest bet in quantum computing at this moment. Or it might be the bet that sounds smart until the ceiling collapses onto it. So here's what I want your honest read on. And I mean actually drop it in the comments. Which bet would you back right now? The wide floor that survives any hardware outcome, or the deep ceiling built for the machine you believe will win? Two genuinely different strategies. Two genuinely defensible answers. Which one wins the pre-winner phase? If you want to follow exactly how the Pilot OS cross-modality claim holds up as independent benchmarks emerge, and whether IBM or Microsoft moves to close the neutral atom gap, subscribe, because that's the specific story we'll be tracking. Three machines so different they shouldn't share a control layer. One operating system that says otherwise. The bet is that it won't have to pick.